What we're going to go over right now is the SN2 mechanism for the reaction of a primary alcohol with a strong acid like HBr. So I'm going to keep a similar backbone to what I had on the last mechanism. And again, we'll react it with HBr in a solvent that is not capable of being a participating nucleophile. The big difference with this reaction compared to the other one is the fact that in the rate determining step, two chemical species are coming together. And the two that will be coming together will be the protonated alcohol substrate and the bromide, which will be our nucleophile. The reason you have two chemical species coming together in this particular mechanism is due to the fact that primary carbocations are highly unstable, and so you don't tend to form them. And this is a mechanism that occurs instead. It has a high activation energy barrier for the nucleophilic attack, but it is lower than the formation of the carbocation for a primary carbocation, so it goes by a different mechanism. You're going to notice some similarities and some differences. So again, I'm going to redraw that alcohol for us and add some HBr here. Now, just as I said with the SN1 mechanism, HBr is a very strong acid, and you can see this by looking at a pKa table, and if you need to, check it out. It is a very strong acid. So when this HBr bond breaks, bromide or bromine will get those electrons because it is the more electronegative element. That's going to produce a proton in solution, which means somebody's going to have to pick it up, and we need that to be a base. So you look over here at the substrate, you need to find an element that is capable of being a proton acceptor, which is the Bronsted-Lowry definition of a base, or an electron pair donor, which is the definition of a Lewis base. The only atom that meets those two requirements is oxygen, and oxygen will donate some of its lone pair electrons to pick up this proton. And as a result of that, we'll make an alkyloxonium ion. Now, just as I said with the SM1 mechanism, this is a weaker acid-base pair. Okay? And you can check that out too using a pKa table. This is still a strong acid. This guy right here is our conjugate acid. And he's still a strong acid, but he is a weaker acid than HBr. So this is the favorable side of this reaction. That's a fast step. Now, just as we'd said previously, the oxygen on this conjugate acid, our alkyloxonium ion, is not happy with the fact that it has a positive charge. It wants to be neutral or negative. And so one of these three bonds needs to go. Now, if you broke an oxygen-hydrogen bond, oxygen is the more electronegative element, and oxygen would get to keep those electrons, and you would go back to where you were before. It's very possible, but it is not productive chemistry, so we're not going to do that. It is possible, but it has to pick it right back up and come here again if you broke one of those bonds. The only other option is to break the carbon-oxygen bond. The problem with doing that, like we did with the tertiary alcohol, is that if we did that, we'd make a primary carbocation. And primary carbocations are not stable enough because you haven't got great inductive and hyperconjugation effects. Those carbon-hydrogen bonds are already polarized toward the carbon. Let me draw this for you, what it would look like. This does not happen. But if you had it, this little carbon here, let me see what I can do for you. It would have hydrogen here, and the rest of the molecule out there. These little hydrogens this bond here, this carbon-hydrogen bond, is already polarized toward the carbon. Okay, so you're not going to get a substantial inductive effect because hydrogen has to keep some of that electron density, otherwise it would pop off as a proton and you'd be in an even worse situation. So there's only so much electron density those hydrogens can give. Now this guy might be able to give a little more, but it's only one carbon group. And so the inductive effects aren't enough to compensate. And in addition, these little hydrogens only have a 1s orbital. There isn't enough electron density here to actually do a decent hyperconjugation, so you're highly exposed on this end. These type of carbocations just aren't possible. And so you got to do something else. But you still got to break this bond. So what happens is that the bromine, this bromide here, is actually going to add at the same time that the carbon-oxygen bond breaks. So this carbon right here, it needs to maintain 4 bonds at all times. And I'm going to show you what that looks like, because it's really important that this carbon maintain 4 bonds at all times. It can't form a carbocation. Okay? Let's see my representation of that. But what's actually going to happen in the transition state here is that the water bond, the carbon-oxygen bond here, will start to break, and those pair of electrons will go to the oxygen. But that can't just leave. It happens as the bromide starts to give its electrons to the carbon. So you're shuttling electron density. This guy is giving electrons to this carbon, while oxygen is taking electrons. It's like going through a door, and carbon's the door. If someone's coming to the door, the guy that's at the door needs to leave in the door in the same direction. They go in a continuous flow. Otherwise, you've got a traffic jam. This is a trigonal bipyramidal structure, is what it looks like actually in the transition state. So the bromine must come in from the back side when this actually occurs. And this is an all-in-one step, and this is how we actually avoid the formation of the carbocation. So when you're all done with this process, you end up making your alkyl halide, and you still have your water at the end. It's just that you did not form a carbocation. We did whatever we had to avoid it. Now it still has a high activation barrier, but again, in this rate determining step right here, this is the rate determining step, this is the slow one, there are 2 chemicals involved. There is the substrate, which is our conjugate acid, our alkyl oxonium ion, and our nucleophile, which is bromide. It's our conjugate base. There are 2 chemicals involved in this rate determining step. And that's why this is called an SN2, because we're still substituting one group for another. We're involving a nucleophile, and it is a substitution reaction where, again, we've got this done.